Ohm's law is always used to analyze simple circuits, a capacitor connected to a source, IC chips. They are all connected in a complicated manner. Point number 1, KCL is also called Hello students, a new sunrise, a new day. Dear friends, belief and confidence are the two tools which will take me to the path of destiny. This is SD Sir again from the Temple of Excellence, Vidhyaashram Pre-University College, Mysuru. What is that we have in store in this session? Completely new concept. Anyone is intending to go for networking, communication in your professional course, this is the base chapter, something called Kirchoff's laws. So my session 8 of the master chapter is completely based on understanding the networks. Fine. So without being late, let us start the beautiful concept called Kirchoff's laws. My dear students, before I take you all into the jungle of networking, let us try to understand the basic difference between Ohm's law and Kirchoff's law. Very simple. Ohm's law is always used to analyze simple circuits. Wherever I had a resistor connected to a source, a capacitor connected to a source, wherever I had single circuit elements, we always used Ohm's law. But on the other hand, Kirchoff's laws are used to analyze complicated circuits. If you observe the slide, students, this is a jumbled up circuit, hundreds of components. ನೀವು ನಿಮ್ಮ ಟೆಲಿವಿಷನ್ ಸರ್ಕ್ಯೂಟ್ ತೆಗೆದು ನೋಡಿದ್ರೆ, ಮನೇಲಿ ಮಾಡ್ಲಿಕ್ಕೆ ಹೋಗಬೇಡಿ, ಎಲ್ಲಾದರೂ ಗಮನಿಸಿದ್ರೆ ಅಲ್ಲಿ ಸಾವಿರಾರು ಕಾಂಪೊನೆಂಟ್ಗಳಿರುತ್ತೆ. ಹಂಡ್ರೆಡ್ಸ್ ಆಫ್ ರೆಸಿಸ್ಟರ್ಸ್, ಹಂಡ್ರೆಡ್ಸ್ ಆಫ್ ಕೆಪಾಸಿಟರ್ಸ್, ಇಂಡಕ್ಟರ್ಸ್, IC chips. They are all connected in a complicated manner. Therefore, I analyze it as a complicated circuit. And therefore, I say, Kirchoff's law is used to analyze complicated electrical circuits. So, my dear students, when I say complicated electrical circuits to be analyzed, what do I actually mean by that? It means we are finding currents and voltages in different parts of a complicated electrical circuit. The very simple understanding of analyzing complicated circuit means we are finding current and voltage in different parts of that circuit. So, my dear students, what is the significance of Kirchoff's law? Using Kirchoff's law, we will find current and voltages in different parts of an electrical network. We are analyzing a complicated electrical network. So the entire summary of bisecting this chapter is, we are finding currents and voltages. We are analyzing complicated electrical circuits. Now, before I jump into Kirchoff's current law and Kirchoff's voltage law, we will study a few important terms that are linked with Kirchoff's laws. The first thing is what I call an electrical network. My dear students, the very word network means something which is complicated in arrangement. ದಯವಿಟ್ಟು ಗಮನಿಸಿ, ನೆಟ್ವರ್ಕ್ ಅಂದ್ರೆ ಒಂದು ಕಾಂಪ್ಲಿಕೇಟೆಡ್ ಕನೆಕ್ಷನ್ ಅಥವಾ ಕಾಂಪ್ಲಿಕೇಟೆಡ್ ಅರೇಂಜ್ಮೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಹ್ಯೂಮನ್ ನರ್ವಸ್ ಸಿಸ್ಟಮ್ is a complicated arrangement of many nerves. Similarly, I am learning electrical network. If you observe this diagram, students, you have resistors, you have capacitors, this is an inductor, which is a coil, batteries. So this is a circuit which has more electrical components in it. Several resistors are present, several capacitors are present. I have connected coils which are called inductors. I have energy sources which are called batteries, and all of them are connected in a complicated manner, exactly as the picture towards the left of this slide. And such a complicated arrangement is what we call as electrical network. I am talking about electrical network. Various resistors, umpty number of capacitors, many inductors, many energy sources. And all of them are not simple in connection. They are arranged in a complicated manner. And that is what we call as an electrical network. Therefore, understand, when I talk about electrical network, it is a complicated electrical circuit. What does it comprise of? Many circuit elements, umpty number of circuit components. There will be resistors, capacitors, coils, batteries, oscillators, and all of them will be connected in a complicated manner, and this arrangement is referred as electrical network. Now, the second one is a very, very important term something called as node, or the node is also referred as junction. Kirchoff's current law is called the law of nodes, the law of junction. Therefore, very important for us to understand what is a node. My dear students, if you observe this diagram, probably an electrical network, I want all of you to concentrate at this point B. Analyze ಮಾಡಿ a point B na ಗಮನಿಸಿ. You will observe that at this single point there is a resistor connected, a capacitor connected, and an inductor connected. Please to note that at one single point I have a resistor connected, I have a capacitor connected, as well as an inductor. It is a junction for connecting more than two conductors. ಆ ಒಂದೇ ಪಾಯಿಂಟ್ ಬಿ ಯಲ್ಲಿ ಒಂದಕ್ಕಿಂತ ಹೆಚ್ಚು ಕಂಡಕ್ಟರ್ಗಳನ್ನು ಕನೆಕ್ಟ್ ಮಾಡಿದ್ದೀನಿ. that point itself is called as node. So my dear students, node in an electrical network is a point where more than two conductors are connected, and it is also called as junction. Again, refer to this point here. I have a resistor, I have an inductor, I have a capacitor. Again, this point is termed as node. So please to know that any point in an electrical network where two or more conductors are connected is what we call as node or junction. Now, the third one is called mesh, or what we also call as a loop. Mesh or a loop. ಕಿಟಕಿಗಳಿಗೆ ವಿಂಡೋಸ್ಗೆ ಮೆಶ್ ಹಾಕಿರ್ತೀವಲ್ವಾ, ಹಾಗಿದ್ರೆ ವಾಟ್ ಈಸ್ ಮೆಶ್ ಇನ್ ಆನ್ ಎಲೆಕ್ಟ್ರಿಕಲ್ ನೆಟ್ವರ್ಕ್? ವಾಟ್ I refer as loop in an electrical network. Again, my dear students, whenever I say mesh or a loop, it is a closed path for the flow of electric current. I repeat again, in any electrical network, if you consider an electrical network a closed path for the flow of current is what I call as a mesh or a loop. Vikramadityan Betala iddange, closed path for the flow of electric current. So if you observe here, A, B, C, D, A, this is called as a mesh. A, B, C, D, A is a mesh. So please know, I am not stopping until D. I am going back to the point A. I am traversing back to the point A. From where I started, I am reaching the same point. Therefore, I am calling this as a closed path. So, in an electrical network, Mesh or a loop is a closed path for the flow of electric current, and any network analysis will happen with reference to these three definitions. My good friends, what was the first one? Electrical network. Complicated arrangement of circuit components. Hundreds of resistors, capacitors, inductors, all of them are jumbled up, all of them are connected in a complicated manner, and such an arrangement is called an electrical network. Then node. What do I call node also? As junction. Why? It is that point in an electrical network, junction in an electrical network where two or more conductors are connected. And finally, mesh, which we also call as loop in any electrical network, the closed path for the flow of electric current is called as a mesh or a loop. And with aid of these three definitions, we will start understanding Kirchoff's laws. A small note here, students, which may be asked for 1 mark. Please do understand, Kirchoff's laws are applied for both AC and DC circuits. If you consider an AC circuit, there again you can apply Kirchoff's law. Again, a DC circuit, yes, again I can apply Kirchoff's laws. So have a thought in mind. Kirchoff's laws is applicable to both AC as well as DC circuits. Now, continuing further. Now, these are very important questions. 2 laws. The first one, what I study as Kirchoff's current law. The second one, Kirchoff's voltage law. Asked in the examination for 2 marks, and if you need to do the derivation on meter bridge or solve any question related to networking, yes, these are 2 important laws. So first I start discussing KCL, which is called Kirchoff's current law. So in short, Kirchoff's current law is called KCL. Point number 1, KCL is also called the law of nodes or the law of junction. I repeat, my dear students, KCL, Kirchoff's current law, is also called the law of nodes or the law of junction, which makes me believe that this somewhere has to be associated with a node or a junction. We will first hear to the statement of this law. KCL says that the algebraic sum of currents, again, not simply current, the algebraic sum of currents, where very clearly at a node in any closed electrical network is 0. Beautiful statement. He says algebraic sum of currents. The currents which flow through a node. The algebraic sum of those currents flowing through a node in any electrical network is 0. Or mathematically we write, at the nodes of an electrical network, summation I is equal to 0. Please to understand, consider any node in an electrical network. Their summation I has to be 0, which means the algebraic sum of currents at that node should always be 0. Now my intention, friends, is to know what is this algebraic sum of currents. You remember electric charges, where we spoke algebraic sum of charges? I just told you all that algebraic sum means taking both the positive sum as well as the negative sum. When I speak of algebraic sum, it is simply considering the positive sum as well as the negative sum. Now this is algebraic sum of currents. Now what is this algebraic sum of currents? When do I treat current is positive? When do I treat current is negative? Which I will gear on with this explanation now. Listen carefully. I consider an electrical network where I have 4 resistors connected and A is the node. Can I call A as the node? Yes. Why? 4 resistors are connected at the same point A. Therefore, it is treated as the node. I1, I2, I3 and I4 are the currents flowing through different parts of that node. So, there is an electrical network. I treat the point A as the node, and I1, I2, I3 and I4 are the currents which flow through different parts of that node. Now listen carefully. By convention, ಇದು ಕನ್ವೆನ್ಷನ್ ಹೀಗೆ ಇರಬೇಕು ಅಂತಲ್ಲ, ಆದರೆ ನಮ್ಮ ಕನ್ವೀನಿಯನ್ಸ್ಗೆ ಒಂದು ಕನ್ವೆನ್ಷನ್ ಫಾಲೋ ಮಾಡ್ತಿದ್ದೀವಿ. ವಾಟ್ ಈಸ್ ದಟ್ ಕನ್ವೆನ್ಷನ್? ಪ್ಲೀಸ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್, ಎನಿ ಕರೆಂಟ್ entering the node is taken positive. Current which enters into the node, current which flows into the node is taken to be positive current. It is a convention followed. And any current leaving the node is taken negative. ಒಂದು ನೋಡ್ ಒಳಗಡೆ ಹರಿಯುವಂತ ಕರೆಂಟ್ ನ ಪಾಸಿಟಿವ್ ಕನ್ಸಿಡರ್ ಮಾಡ್ತೀವಿ, ಒಂದು ನೋಡಿಂದ ಹೊರಗಡೆ ಬರ್ತಿರುವ ಕರೆಂಟ್ ನ ನೆಗೆಟಿವ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡ್ತೀವಿ. ಸೊ ಪ್ಲೀಸ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್, ಕರೆಂಟ್ which enters the node is taken positive, current leaving the node is taken negative. Now by this convention, is I1 positive or negative? Yes, very clearly the arrow shows that I1 is entering the node. I1 is flowing into the node. So I1 is considered to be positive. What about I2, students? Yes, good. I2 is leaving the node. It is going out of the node. So conventionally, I2 is negative. I3 entering the node, positive. I4 leaving the node, which is negative. So, by convention, I1 and I3 are positive currents. Why? Because they are entering the node. They are going into the node. I2 and I4 are negative currents. Why? They are going out of the node. Therefore, I write I1 minus I2 plus I3 minus I4 is equal to 0. Why should it be equal to 0? That is what KCL stated, which told at any node, algebraic sum of currents. Please do consider the positive current as well as the negative current. Algebraic sum of currents at a node is always 0. Or rearranging this, I1 plus I3 equals I2 plus I4. Again, from that expression, I am getting the alternative statement of KCL. What is that? The sum of the currents entering the node should always be equal to the sum of the currents leaving the node. Sum of the positive currents should always be equal to sum of the negative currents at a node. So we have understood, students, at a node, the algebraic sum of currents is always equal to 0. And this KCL is a consequence of conservation of charges. ಪ್ರಶ್ನೆ ಕೇಳ್ತಾರೆ ಪರೀಕ್ಷೆಯಲ್ಲಿ, ನೇಮ್ ದ ಪ್ರಿನ್ಸಿಪಲ್ ಆಫ್ Kirchoff's current law, and Kirchoff's current law is based on the principle of conservation of charges. Or you may also have a question stating that at which point of an electrical network conservation of charges is valid. Conservation of charges always happens at a node, and this is all what you study about KCL. Now, going forward with Kirchoff's voltage law, KVL, slightly absurd to follow, but yes, we will make it very simple and enjoy KVL. Potential law, voltage law. The statement says that the algebraic sum of EMFs and changes in potential. Here, voltage law is concerned with EMF and potential. So he says algebraic sum of the EMFs and changes in potential. I am concerned about EMFs and changes in potential where around a closed loop, again mesh of an electrical network is 0. KCL was framed with node into consideration. KVL is stated with a loop or a mesh into consideration. So, what is the statement of KVL? The algebraic sum of EMFs and changes in potential, EMFs and changes in potential, where in a closed loop, I am considering a loop, closed loop of an electrical network is 0. Therefore, I know algebraic sum of EMF, summation E, EMF, and changes in potential, potential V from Ohm's law is nothing but I into R. So, this is summation I into R should be equal to 0. Therefore, many a times we state this law also as algebraic sum of EMFs and the IR product, changes in potential na IR product antlu karitive, because potential is the product of current and resistance by Ohm's law. So algebraic sum of EMFs and changes in potential, the IR product in a closed loop of an electrical network should be 0. So summation E plus summation IR is equal to 0. Now, there are two rules that we follow to apply KVL to a network. The first rule says the EMF is taken positive if it sends current from negative to positive terminal. When do you take EMF of a cell positive? If the current is flowing from negative to the positive terminal of the cell. Else, EMF is taken negative, which means if current flows from positive to the negative terminal, then EMF of the cell is always considered to be negative. Again a convention. So when is EMF positive? If current flows from negative to positive terminal. If EMF is negative, that is when current flows from positive to negative terminal. Second one, the IR product is taken negative if the direction of current is along the direction traversed. Else, it is positive. Don't worry, going to the linguistic part of the second rule, I will analyze this network using KVL and then you will understand the second rule. Now, I will apply KVL to the mesh A, B, C, D, A. So please to understand, I am applying KVL to the mesh A, B, C, D, A. And this is the direction of traverse. Direction of traverse is the path that is given by the paper setter. It is some path in which current is believed to move. So, if I try to complete this path, this is how it moves. Now, which are the currents that flow through this mesh? I1 and I2. Can I consider I3? No, I3 is the current flowing in the other mesh. So in whatever mesh I have considered, the currents flowing are only I1 and I2. And the resistances present here is R1 and R2. And the EMF of the cell is E1. Now all of you observe, ದಯವಿಟ್ಟು ಗಮನ ಇಟ್ಟು ಕೇಳಿ. I1, look at this direction of I1. Is it along the direction of traverse? Is it in the same direction given? Please to analyze. See, this is the direction of traverse. This is how the direction of traverse is happening. But I1 is flowing in the opposite direction. So I1 is opposite to the direction of traverse. So please know, students, if the direction of current is opposite to the direction of traverse, if current is flowing opposite to the direction given, then the product of current and resistance there is always positive. So here this is I1 R1. Why direction is always positive? Here I1 is flowing opposite to the direction of traverse. Whatever direction is given, I1 is opposite to it. Therefore, it is I1 R1. The product of current and resistance is positive. What about I2? Again, if you observe, I2 is in this direction and the direction of traverse is opposite to it. Again, product of I2 R2 is positive. So learn, students, if the direction of current is opposite to the direction of traverse, as in this case, the IR product is always positive. If it would have been in the same direction, IR product will be negative. Now what about the EMF? See, current is flowing from the positive to from the negative to the positive terminal. Don't observe the entire network. E1 terminals of the cell. Current flows from negative to positive terminal. Therefore, EMF is positive and this should be 0 according to KVL. Similarly, you will analyze the second part of the mesh as an assignment. So I have taught you all how to apply KVL. The first mesh I have solved. I want you all to observe and analyze the second mesh. And please to understand, KVL is the consequence of conservation of energy. So in this particular session, we understood what is a network. We understood what is a mesh, loop, which are the same. We understood node and junction. What did KCL state? At any node of a network, algebraic sum of currents should be 0. What was positive current? Current entering the node. Negative current? Current leaving the node. So what did we say? Sum of the currents entering the node should be equal to the sum of the currents leaving the node. And it was the principle of conservation of charges. KVL told algebraic sum of EMF and changes in potential around a closed loop of an electrical network is 0. With this, in my next session, I take up a very important discussion called Wheatstone's network based on these two laws. Hope you appreciate and come prepared for that. Until then, stay tuned. Goodbye.